Welcome to AI Paper Podcasts. Today, we're diving into a really fascinating paper, Deepseek R1. It's all about pushing reasoning capabilities in LLMs, mainly through reinforcement learning.
Yeah, this one's a big deal. It tackles that core question.
Yeah.
Can you get an LLM to reason, like really reason, mostly with RL, cutting down on all that supervised data?
Exactly. And while they kind of answered it, let's do the quick summary up front for, the short clips. First up, there was DeepSeek R1-Zero.
Right, the pure RL experiment. No supervised fine-tuning at all.
And it worked. It showed this amazing emergence of reasoning. We're talking 71.0% pass at 1 on the AME 2024 math benchmark. That alone is huge. Proves pure RL can do it.
Definitely a foundational finding. Just pure self-evolution kicking in. Yeah. Then they built on that with the full DeepSeek R1.
Right, the refined version. Multi-stage process. Started with a bit of supervised data, a cold start, they called it then, iterative RL, to fix things like readability and weird language mixing R10 had.
And that polished R1, it performed right up there with models like OpenAI's O1 1217, like 79.8% on AME 2024, 97.3% on Math 500. Really impressive stuff.
And maybe the biggest news for many of you listening, the open source angle. They released R10, R1, and 6 dense models from 1.5 billion up to 70 billion parameters.
All distilled from R1. Which is key, right? It shows these complex reasoning patterns they found in the big model. You can actually transfer them pretty efficiently to smaller, more practical models.
Yeah, that distillation part is potentially a game changer for getting this power out there without needing, nation-state levels of compute for inference.
It's what everyone's looking for, high performance, manageable cost.
Okay, so let's rewind a bit. DeepSeek R10, the pure RL thing. What was the thinking there? Why start with just RL?
Well, they wanted to see what the base model, DeepSeek V3 base, was capable of on its own. Like, could it learn to reason almost from scratch just by being rewarded for getting the right answers? Pure self-evolution.
Kind of like, can it teach itself to think if the incentives are right?
Exactly. And for the RL algorithm, they use something called GRPO Group Relative Policy Optimization. Not the usual PPO or DPO we hear about.
GRPO, why that choice? What's different?
It seems like it was mainly about efficiency. GRPO manages to skip the critic model. Usually you have the policy model and then a whole separate critic model judging its actions.
Right, which doubles the model size during training, basically.
Exactly. GRPO estimates the baseline, the advantage, by looking at scores from a whole group of generated outputs. It avoids needing that second big model.
Okay, so it saves compute, makes sense for large-scale experiments.
Definitely. And sticking with that theme of simplicity, their reward system for R10 was, well, almost basic. They deliberately avoided using complex neural reward models.
Why? To avoid reward hacking, or just keep things simple?
Both, I think. Prevent reward hacking, yeah, but also just keep the pipeline cleaner, more focus on the core reasoning task.
So what did this simple rule-based reward look like then?
Just 2 things, really. First, accuracy rewards. Super simple checks. For math, did the final answer appear correctly in the specified box format? That's it. For code, did it compile and pass tests? Pass, fail.
No partial credit for getting close?
Nope, just the final output accuracy. Yeah. And the second reward was just for format.
Format, like how pretty the output looked.
Sort of. It just enforced that the model's thinking process, its chain of thought, had to be wrapped inside think and think tags.
So incentivizing it to show its work, right, basically. But not judging the quality of the work itself, just that it showed it.
Precisely, just the structure. And these 2 simple rewards, combined with letting the model generate longer outputs, more thinking time, led to this aha moment.
Yeah, that part in paper is really cool. You look at figure 2, the performance chart for AIM, and it just shoots up from like 15% baseline to over 70%. What happened there?
As the model was allowed more test time computation, basically more steps to think, it started doing things spontaneously. Like it started reflecting on its own answers, verifying them, even trying different approaches if the first one didn't seem right.
It learned that thinking harder, or maybe smarter, actually paid off in terms of that simple accuracy reward.
Exactly. It learned to self-correct. And they have that amazing example in Table 3.
Oh yeah, the quote. It's almost human.
Right. The model's mid-thought process, and it literally outputs, wait, that's an aha moment I can flag here. Let's reevaluate this step by step.
Incredible. Just from being rewarded for getting the answer right and showing its work in tags.
It really shows the power of just incentivizing thinking time and accuracy, even with simple rules. That 71% AME score is the proof.
But like you hinted, R10 wasn't perfect for actual use, right? Which brings us to the full DeepSeek R1 pipeline. What were the big problems with R10?
Yeah, it was powerful but messy. The chain of thought output was often hard to read, badly formatted, and the killer was the language mixing.
Language mixing.
Yeah, you'd get Chinese and English mixed together, sometimes mid-sentence, within the reasoning steps. Made it pretty much unusable if you actually wanted to follow its logic.
Okay, yeah, that's a showstopper. So for the full R1, they needed to fix that. They started stage 1 with a cold start SFT. Why SFT if RL was the star?
It was a small, targeted SFT stage. They used a bit of high-quality, long chain-of-thought data right at the beginning. The idea was to basically teach the model good habits about readability and structure before unleashing the large-scale RL.
Sort of like giving it some guardrails before it started exploring.
Exactly. Stabilize it first. Avoid that early messy phase R10 probably went through. And this SFT data specifically enforced a clear output pattern.
What pattern was that?
It was special token reasoning process, special token summary. So it forced the model to always provide a concise summary at the end, separate from the detailed reasoning, much cleaner.
Gotcha. So stable base, clear format, then stage 2, back to RL.
Yep. Large-scale RL, again, focused on reasoning tasks, math, coding, science, similar to R10. But this time, they tackled the language mixing head-on.
How did they manage that? Another reward.
Yeah, they added a specific language consistency reward. It basically calculated the proportion of words in the chain of thought that were in the target language, say, English.
And just added that score to the accuracy reward.
Correct. So the model was incentivized to be right and to stick to one language while thinking.
Did that hurt performance? Usually enforcing constraints like that costs something.
It did, slightly. They mentioned a small performance dip compared to letting it mix languages freely. But obviously, the usability gain was huge, a worthwhile trade-off.
Makes sense. Okay, so after stage 2, it was good at reasoning, clearly, but they needed to make sure it was still good at, other stuff. Stage 3.
Stage 3 was about bringing back general capabilities and refining the reasoning data. They used rejection sampling on the RL model's output.
Filtering out the bad stuff.
Yeah, they generated a lot of reasoning samples and filtered out the ones with chaotic or mixed language thoughts, keeping about 600,000 good ones. Then, critically, they mixed in about 200,000 non-reasoning samples.
Like what?
Things like writing tasks, factual Q&A, general knowledge, self-cognition stuff. They actually reused a lot of data from the original DeepSeek V3 SFT dataset here. This whole mix was used for another round of SFT.
Ah, so an SFT stage to broaden its skills beyond just pure reasoning.
Exactly. Keep it well-rounded. And then finally, stage 4 was one more RL phase, but this time focused on alignment.
Helpfulness and harmlessness, the usual suspects.
Right. Polishing the final behavior. Interestingly, they used different reward strategies here. For the reasoning data, they stuck with the rule-based accuracy checks.
Okay.
But for the general data, they brought in standard reward models like you'd expect for alignment. But they did something clever.
What was that?
For helpfulness, the reward model only looked at the final summary part of the output. Summary. For harmlessness, it looked at the whole thing, including the chain of thought.
Why only the summary for helpfulness?
The thinking seems to be, they didn't want the helpfulness alignment to mess with the complex reasoning process discovered in stage 2. Let the reasoning part be optimized for accuracy and align the final presented answer for helpfulness.
That's quite nuanced, separating the thinking from the presenting for alignment.
Yeah, it's a really interesting approach to avoid damaging the core capability while still making it user-friendly and safe.
Okay, let's talk results. How did DeepSeek-R1 actually stack up against the competition, like OpenAI's O1 models?
Extremely well, especially in its core areas, math and code. AME 2024 pass at 1 was 79.8%, just edging out O1 1217. Math 500 was 97.3%, basically on par.
And coding.
Codeforce's rating was 2029 ELO. That's seriously strong, like 96th percentile compared to human competitors.
Wow, so the RL focus really paid off there. Did it generalize well beyond those exam-style tasks?
It seems so. Big jumps over the base DeepSeek V3 on general knowledge benchmarks. MMAU hit 90.8%, GBQA Diamond, which is super hard, got 71.5%.
So learning to reason helped it across the board.
That's the implication. And on general chatbot evils like AlpaCable 2.0 and Arena Hard, it scored really well too, showing it's generally capable and helpful.
Any areas where it didn't shine as much?
Yeah, there was an interesting point about Chinese Simple QA. R1 actually did worse than the base V3 model.
Really? Why?
Because of that final safety alignment stage, stage 4 RL. It made the model more likely to refuse to answer certain queries. They noted that without that final safety RL, R1 could smash that benchmark, getting over 70%.
The classic safety utility trade-off biting them.
Exactly. It's always a balancing act. But it did well on things like instruction following, IF evil.
Okay, that's R1. Now, the distillation part. This feels really important for practical use. How did they do it?
It was surprisingly simple, actually. They just had the big DeepSeek-R1 model, generate about 800,000 examples, reasoning, general tasks, the whole mix.
Okay, create a data set using the teacher model.
Yep. And then they just used standard supervised fine-tuning, SFT, to train smaller open source models on this data set. Models like Quinn 2.5, the Llama 3 series, no extra RL in the small models.
Just SFT with the R1's outputs.
That's it.
And how well did that work? Did the reasoning transfer?
Remarkably well. A distilled Quinn 7B model got 55.5% on AME. The distilled 14B Quinn model actually beat a much larger 32B competitor model on all metrics they showed.
Wow, so the 14B was punching way above its weight.
Totally. And their distilled 32B and 70B models significantly outperformed OpenAI's O1 Mini on most reasoning benchmarks. It really shows this SFT distillation approach is super effective for transferring these capabilities.
This gets to a really critical point they tested, right? Is it better to distill from a big model, or could you just run large-scale RL on the smaller model itself to get similar results?
Yeah, they did that direct comparison. They took a Quinn 32B base model, version 1. They fine-tuned it using SFT distillation from DeepSeek-R1 version 2. They fine-tuned the same base model using their pure RL approach like R1-Zero.
And the result?
Big difference. The distilled 32B model hit 72.6% on A. The pure RL-trained 32B model, even after tons of RL steps, only reached 47.0%.
Okay, that's conclusive. Distilling the reasoning patterns discovered by the giant R1 model is way more effective and probably much cheaper than trying to get a smaller model to discover those patterns itself via RL.
It really suggests that discovering these complex reasoning pathways might fundamentally require that massive scale.
Right.
But once discovered, they can be taught quite effectively via distillation.
Fascinating. They were also upfront about things that didn't work on the way to R1. What were some dead ends?
Two main ones they highlighted. First was trying to use a process reward model, or PRM.
Rewarding intermediate steps?
Yeah, the idea is to reward correct steps within the chain of thought, not just the final answer. But they found it really hard to define what a correct step is for general reasoning. Plus, verifying those steps is complex, and it's prone to reward hacking. Too difficult and costly to scale.
So outcome-based reward was just more practical. What was the other failed path?
Monte Carlo tree search, MCTS. The technique that worked so well for AlphaGo.
Why didn't MCTS work here?
The search space is just too vast. In games like Go or chess, MCTS explores a huge but ultimately finite tree of moves. For language generation, every token choice opens up an almost infinite branch.
Way bigger than a game board.
Exponentially bigger. Yeah. And training a value model to effectively guide that massive search iteratively just proved intractable. Too complex, too much compute.
Makes sense. So looking ahead, what limitations did they acknowledge for the final DeepSeek R1 model? Where's the future work?
One key thing is prompt sensitivity. They specifically say R1 works best with zero-shot prompts. Adding few-shot examples actually hurts its performance.
That's unusual. Any idea why?
Maybe the RL process optimized it so heavily for its internal reasoning flow that external examples just confuse it. Hard to say, but it's important for users. Zero-shot only.
Good tip. What else?
They mentioned RL hasn't really cracked complex software engineering tasks yet. R1's performance on things like the ADER benchmark is still behind models like O1 1217.
Still room to grow there.
Definitely. And that language mixing issue, while much better, is still a potential problem for languages other than Chinese and English.
Okay.
And finally, some general capabilities like really complex function calling or intricate role-playing scenarios, areas where the base DeepSeek v3 might have been stronger, R1 might lag a bit. There's still that trade-off between hyper-optimizing for reasoning versus maintaining broad general skills.
Right. So wrapping this all up, the big takeaway seems to be that DeepSeek R1 really validates this multi-stage pipeline, heavily anchored by RL. It shows you can bootstrap reasoning from a base model, maybe even purely with RL initially.
And then refine it, make it usable, and critically, distill that hard-won reasoning capability down into smaller, more deployable models very effectively using just SFT.
They've kind of laid out a potential roadmap. Discover the complex stuff with massive RL, then distribute it via distillation.
Seems like a very powerful paradigm.
Which brings us to that final kind of mind-bending thought. If these high-level reasoning patterns are so hard to discover, maybe only emerging in the biggest models, and so hard to replicate even with extensive RL on smaller models, what does that say about the cost of AGI or advanced AI?
Yeah, it poses the question. Is the real bottleneck, the true cost, not just pre-training data or parameters, but the sheer computational scale needed to discover these fundamental cognitive patterns in the first place?
Implying that maybe smaller models can only ever be echoes or approximations of the intelligence crystallized within the absolute largest computational shells we can build.
It strongly suggests that for discovering genuinely new cognitive leaps, that massive scale might be non-negotiable, at least for the initial breakthrough. The distillation then makes it accessible.
Definitely something to mull over as we watch these models continue to scale. Thanks for walking us through this paper. Really insightful stuff.
Absolutely, my pleasure. It's a fascinating piece of work.